Hello, everyone. Sorry, my computer was a little delayed pulling you up. I was also checking to make sure I could share screen with my iPad again. It seems to be working. Evidently I got to shut down both of my Wi-Fi's on my computer as well as my iPad before I actually try to link the two. I don't know why, but it's getting hung up in that. So if I just restart it and just turn off my Wi-Fi for a second, turn it back on, that fixes it. Anybody have any questions before we get started? I'm in the process.
Anything about like topics and such?
Yeah, it could be course topics. It could be stuff about the syllabus. It could be stuff about homework.
Well, I was regarding course topics. Are we going to be going over the whole order of magnitude and all that today?
Yeah, I'm going to talk a little bit about that. We don't really do too terribly much with it, but if you really want to learn more about it, you'll see when you start taking the practice test what kind of questions we're asking you, and that's as good an example as any. But if you really want to look into further understanding how to do that, there's a book called Guesstimation 2.0 written by a professor at ODU that's quite good. The library has it. You can check it out a little bit. But basically what you try to do is if you don't actually know that much about what the object is that they're trying to get you to estimate, like one of the estimates might be take the room you're in and estimate how many houseflies could you fit in it. So you might not necessarily know how big a housefly is, but you could do something like, is it 1 centimeter long or 10 centimeters long or less than 1 centimeter long? So what you can do is sort of take the limit of how small it could be to the limit of how big it could be, multiply those two and take a square root. That's a very typical way of doing that. It's called the geometric mean. So for instance, y'all probably know a housefly is about that long. Okay, a housefly, for instance, is going to be about that long. That's close to a centimeter, but it's not a full centimeter. So maybe you go 0.1 and 1. Something's asking about closed caption. I want everybody to maybe save and share with that other apps. Yes, I'm good with that. Okay, someone asked for closed captions, and I'm cool with that. I know they're not that good, but it's probably better than nothing, and me talking fast might not help the situation. So it looks like everything's going okay now. So you might say, well, I think the fly is definitely bigger than 0.1 centimeters, but maybe not as big as 10 centimeters. So notice that's one order of magnitude, 0.1 to 1. So if you multiply 0.1 times 1, and then take the square root of that, you can use that to one non-zero digit as the size of the fly. And that would be his length, say. And then you might be a little more knowledgeable about what its width is. Maybe you say its width really is on the order of a millimeter. So you can say his volume would be square root of 0.1 times 10, times 1, which would be square root of 0.1. And then you could say his width is 0.1, his height is 0.1. And then you just take and say, well, I guess this room is 3 meters to 4 meters. I don't really know for sure. So you can do, again, the geometric mean. 3 times 4, take the square root, and that'll be the width of the room. And then another dimension for the length of the room, maybe that's between 4 and 5. So you go square root of parentheses 4 times 5. And then, of course, make sure your fly is in units of meters, not cubic meters, not centimeters, or that your room is units of centimeters. And then you say the height, of course, of the room is probably 3 meters. Obviously, most houses are 8 foot. A lot of houses nowadays have 9-foot ceilings. So 9-foot ceiling is pretty close to 3 meters. So you could do that. Then you just take the volume of the room divided by the volume of the fly that you estimated, and that should be able to give you an estimate of how many flies fit in a room. That's about as complicated as it really gets. You'll see there's a lot different types of questions that your book uses in the test bank. So definitely look at the practice test, and you'll be getting some questions like that. I think some of the more typical ones is, how many times would your heart beat in a century, or how many times your heart beat during one trip around the sun, little stuff like that. But it's always a matter of you're not measuring stuff. Yes, go ahead.
I was going to say, I did do the practice quizzes in the
Mhm.
in Pearson,
Right.
and they were very unhelpful. They like it was basically like, hey, how many people can be in the Pentagon? And I looked up the area of the Pentagon and tried to calculate from that, and then they give you the like once you get it wrong enough times, they give you the answer, and they say, oh, you're supposed to figure out the actual like area in the Pentagon, but then you have to subtract all the space
In the middle.
that can't be stood on. And I'm sorry, I'm just sitting there thinking, did y'all send me the floor plan for the Pentagon? I didn't notice.
I mean,
Yeah.
on that, I just looked up the square footage of the building, and then assumed that a person needs a square meter of space, because you can't stack people, so it's only like what they can the floor they can stand on. So you have the square foot well, meters. Why I use square meters of the building, and then of course if it's 1 square meter per person, every square meter is how many people you fit. So I don't remember what it came out to be. It was some giant number, but it was pretty much was the square meter of the Pentagon.
Yeah, that's a
I
good
got it in
way
the,
of doing it.
I got it in the ballpark. It's just
Yeah, there's a lot of room for error there.
I was kind of surprised that my master didn't give like it was like, hey, you have to like look this up. I was surprised that the my mastering course actually made us look it up and not provide like at least the way I'm used to it. It normally provides the information you need for the questions. So
Yeah,
I was like,
there wasn't a hint
this up?
for
It's
it
just a
either.
guess. Like,
Was there not a hint for it as well?
no, they didn't have any hints on it. It just
the hints are very vague and broad, so useless.
yeah.
Well, I'll tell you guys.
And
when
this
you're-
one on my calculus, the calculus course doesn't have examples.
Yeah, I'll tell you when you're doing stuff like on a homework, we in the physics world just assume you're going to be Googling a lot of stuff to find out dimensions. When I give you a problem on say a test for a estimate problem, I'm assuming you're going to know that, or it'll be like I for instance left my textbook laying on the front of the desk, and you guys can look at it and see it, but I won't let you come up and measure it. I'm just going to say you need to estimate that. So that's the kind of stuff I tend to stick to. And I'm also a little lenient because sometimes students don't remember the number of, let's say, days that it takes for the Earth to orbit the sun. They might forget that. They come to me and because they might think it's 24 hours, and then I tell them it's about 365.25 days or something like that, and I'll give it to them. So that's more like what you got to worry about. I wouldn't worry too much about a problem as specific as that. And that was on the Pearson homework site, not the practice tests, right?
I've encountered it on the quiz, but I haven't been able to get into the practice test. It says it closed down in January.
Okay, well, let me fix that right now because I thought that was taken care of. I'm going to pull that up right quick. There's like sometimes 3 or 4 places where you can set the dates that things are available. And if I don't remember every area where you can set it, I will forget. So that's a very real possibility. I'm clicking on practice 01, chapter 1 and 2. I'm going to edit the settings. Yep, it said January 31. This must have been one that I missed. Okay, so I'm going to set this to, I think your test is due the 5th. And definitely, you might have already emailed me, but definitely feel free to text me when something like this happens, because that's literally standing in the way of you being able to do work and start prepping. So I don't mind at all if you send me a text message over that, or if you just want to email me and wait. So I'm going to set this now to September 5th at 11:59 p.m. So you'll have access to it throughout the whole day, September 5th. And actually, I'll make September 5th. I'll make sure test 1, which is an online test, I'll make sure you have that through September 5th. Even though we normally make things due on Sunday night, I want to make it due on Monday night. Okay, I fixed that. Thanks for letting me know. Jamie, I think it was. Yeah, Jamie McLaughlin. Keep moving up from under me. I can't find the name. Yeah, it's gone. But yeah, and don't feel discouraged, McLaughlin. That's it. Okay. Yeah, and don't feel discouraged if a question like that throws you. I mean, it should. If you didn't actually know that stuff and you didn't understand the rules with Pearson, that's on me. It's not your problem. but I will say that's a very typical type of thing we'll ask you. It's more like the examples I gave, how many flies can you fit in a room, or how many marbles is there in a pickle jar, or something like that. And if I said something as vague as a pickle jar, then you would be prompted to ask me, well, exactly what kind of pickle jar? Because our jars and refrigerators are this big, whereas the pickle jars you have sitting out on counters in country stores are big suckers. And I would have a ready answer for you on that. Again, it's always within a power of 10 roughly. So I don't expect answers to be like 100 and 105. That shouldn't be the case, nor should it be like 100 and 300. Those are too close together. But 100 versus 1,000, that's probably acceptable. Or 100 versus 10, that's probably acceptable for two answers. So it really is supposed to be an order of magnitude. And the rule is you really only use one non-zero digit. It's almost always better to just like use 200 or 800 or 8 or 2 or 3 or something like that. Any other questions? Things you should know. I would say you probably should know roughly the population of the U.S., roughly the population of the world. The U.S. is looking at about 370 million. The world's about 7.5 billion. Those are just typical numbers. I know, just being a nerd citizen of the earth that watches, news and stuff like that. That's not unacceptable, or that's not too mean to ask. But again, if you're in a test situation that's a little nerve-wracking, you can certainly ask me and I'll let you know. Anybody have anything else? That's a good question, by the way, Jamie. And thanks for your answer. Was it that Jamie too that answered? Or was it Jonathan or something? Horrible name.
I mean, I was talking a little bit.
Okay. Right. Oh, that. Yeah, I was looking for it. But anyways, yeah, thanks for stepping in. I do like that. And I do like you guys working together over homeworks and practice tests. I definitely want y'all to work with each other as much as you can. Almost every semester, I get one or two people will make a study group that gets together either virtually or face-to-face, and they work on stuff, a couple of days before the test. I definitely recommend you do it. It's good for you. And most times you will find there's one or two people that really know sort of everything that's going on, and they feel like they're not really getting anything out of it. Be advised, I've been that person before, and there's going to be some point in the semester or the 2-semester sequence where you're going to find that someone else knows a part that you don't know. Like my big thing when I was taking physics was I didn't know anything about electricity and magnetism, but I knew knew mechanics very, very well. Then when I got to the second semester, some of my friends who were really horrible at virtually everything we did before were really good at electronics. So they'd been doing stuff since they were kids with electronics, and they helped me immensely. So that does happen. You don't have to look at it as keeping score or anything, but you explaining it to people in ways that make sense, make you better understand it. Because if you can't explain it to someone, you don't understand it that well. There is a famous story. Richard Feynman had won the Nobel Prize in physics, and he was working at Caltech. And the chair of the physics department said, "Hey, we'd really like you to come and teach a class on electron spin to our freshman physics teachers, on quantum electrodynamics to our freshman physics students." And he said, "Okay, yeah, let me look into that. I'll get back with you." He's like, "Okay." And then about 3 months went by. And he came to the chair, and the chair said, "Hey, how you doing, Richard?" And Richard said, "Well, I've been thinking about about you asking me to teach that thing." He said, "Well, I just assumed you decided not to." He said, No, I hadn't decided not to. I really wanted to do it, but I don't understand quantum electrodynamics well enough to explain it to freshmen yet. So I don't think it can be done." That was a Nobel Prize winning physicist who won the Nobel Prize partly for his work in quantum electrodynamics and creating it. So for him to say, "I don't understand it well enough to explain to the freshmen," tells you something that really your holy grail of understanding is your ability to teach it to someone that doesn't know anything about it. So keep that in mind when you're trying to learn the material, or especially if you're in a study group. All right, now should have a thing that says download. Okay, there's some chats going on online. Okay. Did you allow formula sheets for midterm and finals? Yes, I do allow you formula sheets. If you want to type up your own, that's great. If you want to handwrite your own, that's great. And I recommend you using the same one and just adding to it, because all tests in physics are comprehensive. Even if they're not meant to be, they're going to be comprehensive. So definitely you can do that. And that is for the midterm and the final. Were y'all able to get the book open? I know I can from my side of Pearson at my lab and mastering. Anybody else have any difficulties with that? Looks like everybody's okay, I guess then. Yeah, I would definitely say that. In fact, what I would recommend you do is keep your work and even turn it in with me if you disagree with what, because I'm going to try to do the test on an online situation where you can immediately look and see what you got wrong. It won't tell you the right answers, but if you come to me immediately after and say, this is my calculation for number such and such, could you look at that and tell me if you think it's wrong enough to get a complete wrong answer? I will completely do that. The downside of multiple choice tests is exactly that. I don't see your work. You might have had very good reasons for making the answer you did, and all the physics might have been done right, and it could have been something as simple as you put it in a calculator wrong. That's just happened. So if you find one or two problems like that on an online test, by all means, write your name on the worksheet that you did, on the sheet where you wrote your work down, and write the number of the problem on there, and then bring it to me right after class, and I'll hold on to it and check it versus your test and bring it back to you the next day. So I don't mind that at all. Mike asked everyone, how did you get to the book? I know when my lab and mastering, you go to the left-hand side and it says e-textbook or it's a longer word than it just used to say e-text, but now it says something weird. So I don't know what it is out of memory. Let me see if I can open it up and figure it out. That'll be fun. Oh, by the way, I'm in the process of, actually, I guess it just finished. Remember our class, my browser crashed at the beginning? Well, it came back, and it actually had recorded that part. So I put that part in my online webpage as well. Yeah, it says Pearson eText on the left-hand side. If you just click on the My Lab and Mastering link on the top left-hand side of your Canvas course, it will say, it'll bring up a gray Mastering Physics box on the left-hand side, and it'll have words like my courses, course home, syllabus scores, purchase options, Pearson eText, study area, document sharing, user settings, and stuff like that. But the Pearson eText is what's there. Let's see. Yeah, that's it. 4 tab down. I'm mastering. Yep. I'm just looking at the chat to see if anybody said anything that I need to address. Looks like y'all are handling each other pretty well. Yeah, generally physics 2 is harder than physics 1, mainly from a mathematical standpoint. I mean, I set you up in my 241 classes. I try to be as pseudo harsh on you as possible. Like I make sure you, for instance, do vector algebra, and I even bring in some vector calculus just to get you used to it. And then in the second semester, we start out of the box with vector calculus. You're going to be doing curls, and take curl under an integral. You're going to be doing dot products and divergences. Divergence is basically a differential equation, and a curl is a differential equation as well, but they're god awful ugly. But they're pretty easy to deal with once you learn the words and what they mean. So yeah, it does get a little harder. But that being said, some people actually think the second semester is easier just because they're good with electronics or they're good with that branch of mathematics, which generally isn't covered, if at all, in the third semester of calculus. I didn't get it in my third semester of calculus. I got the gradient operation and the multifunction chain rule. That was about as far into vector calculus as I was able to get with my 1, 2, and 3 calculus courses. Anything else, anyone? All right, well, what's going to happen now is I'm going to go ahead and start into covering chapter 2. The things I didn't do much with, as you saw, I did explain them a little bit in writing, and I did give you some a video to watch. So by all means, if you still want extra time on that, let me know, and I can do an office hour with you via Zoom or at school. The main thing is there's sort of three things. There's dimensional analysis, and then there's unit analysis. What you have to remember is whenever you have an equation, the numerical value of the equation has to be equal to the numerical value of the other side of the equation. The other thing that's equal is that the units have to be the same. So you can't have 104 meters on the right and 104 joules on the left. That doesn't work because a joule and a meter are not the same thing. You also learn when we get into vectors that you also have something else. So if it's a vector equation, you have to have the magnitude and the direction equal on both sides. So the magnitude on this side has to equal the magnitude on this side. The direction on this side has to equal the direction on this side. And if you're using units, which you are almost always are, the units on this side has to match the units on this side. So it's just the nature of the beast. But that being said, that gives you a whole way of trying to figure out how does, for instance, energy relate to what I showed you last time was mass and velocity, or mass and the speed of light. And in one case, you got really close to the right answer, which is when you're trying to consider how energy of motion is really calculated. We found mv squared when in fact the real result is 1/2 mv squared. But in the case of relativity, where you said, how does energy relate to mass and the speed of light? We got exactly the right answer, which was mc squared. So if you're using the actual units, which are kilograms, meters, seconds, Kelvin, centigrade, or Celsius as we call it, or moles, or any of those kind of things, then you're using unit analysis. If you instead replace the unit of mass with a capital M and the unit of length, or the dimension of length, with a capital L, and the dimension of time with a capital T, then you're just doing dimensional analysis, which is generally a little better anyways. It's not going on the assumption that this is true only in the SI system or only in the British system. So that's the only difference. And you can use that to, one, test to see if an equation makes any sense. So like if you wrote down an equation that you didn't quite remember as 1/2 AT plus V0T plus X0, you could immediately look at the units of that and say, no, that first term's wrong. Okay, that first term's wrong because 1/2 AT has units of not meters, but meters per second. Okay, so that's the main thing you have to get to that. And I think the book does a good job, and also the videos I've shown you, or I advise you to look at, they should help you as well. The other thing, so that was the two of them. The other thing was what we just talked about there, which was estimating things. And I've given you a little bit of a rundown on that. I've pointed you to a book that's helpful. Know that I'm not going to ask you too many of those. I love them. I love to do those problems. For instance, there's a great conceptual physics course textbook called Science and Technology for Future Presidents. It was made into a layman's book by the same guy, but he made a textbook out of it and teaches at UC Berkeley. And this student of his happens to be at a dinner party or something with her parents, and this guy says, you couldn't cover the state of Texas with solar panels and expect to supply the power needs that we have in America. And the girl corrected him and said, no, I think you could do it even smaller than the state of West Virginia. And she did a quick back of the envelope calculation. That's the kind of calculation that we're doing there. And that is a very powerful thing, because you can get, within a factor of 10 of a true estimate. So just keep that in mind, but it's really sort of the holy grail of what you can do after the course is finished, not so much during the course. Okay. And they give an example or two in virtually every chapter. So you'll see examples as the semester goes. And the more fun part is just to pull them out when you're talking with people about stuff. All right, any questions? Okay, so I want to think about kinematics now. I want to talk about the equations that tell how motion depends on things like time, velocity, acceleration. We're not going to think so much about how we make that motion. How do I get a ball to accelerate at 3 meters per second every second? Or how do I accelerate a ball up to 4 meters per second? We're not going to talk about that. That's dynamics. We're going to talk about let's assume the ball has initial velocity and initial acceleration. How far is it going to go in 3 minutes? How fast will it be going after 2 seconds? That kind of stuff. So in order to do so, we need some definitions, and the definitions we need are things like displacement versus distance and position versus distance. So what I'm going to do is open up my document and hopefully share a screen with you. So let's do share screen. Hopefully this opens right up and everything works well. All right, that worked well. So if you imagine a person that started off at x equals 0 at t equals 0, maybe at t equals 1.00 seconds, x was equal to 1.5 meters per, just meters. And then at t equal 2.00 seconds, x was equal to 3.0 meters. And t equals 3.00 seconds, x is equal to 4.5 meters. And let's say dot, 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 dot. We see a pattern, in other words. So what I'm going to do is I'm going to make a graph of position x. I think it's not that. X in meters versus t in seconds. Okay, I'm going to assume this is right on this line. So this is 1, this is 2, this is 3, this is 4, this is 5, 6, 7, 8, like that. And this is 1 second, 2, 3, 4, 5 seconds, 6, 7, 8, 9. Now, if we make a plot of this data, we know at t equals 0 seconds, it was at x equals 0. So I'm going to put a dot right here. We also know that at 1.5 seconds, or excuse me, at 1 second, it was at 1.5 meters. So I'm going to put a dot right here. And then at 3 seconds, it was at, excuse me, at 2 seconds, it was at 3 meters. So I will go up to here. And then at 3 seconds, it was up to 4.5, which is right here. Okay. Now, if I go up another second, it should go up again. And this time it'd be 5.5/6. So if I go up to 4 seconds, it's going to be up to 6 right here. Now, I can take that and say that's my data points. And what I've made is, in fact, a graph of position versus time, and it looks like a straight line. And in fact, it is a straight line, and this is an example of non-accelerated motion. The only time you get a curved x as a function of time, or a curved position as a function of time, is when there's actual acceleration. And that acceleration you might not have a good feel for right now, but just know that it means your velocity is definitely changing. Okay, so we found that after 1 second, an object would move 1.5 meters. After 2 seconds, it moved 3. After 3 seconds, it moved 4.5. After 4 seconds, it moved 5. And we made a plot of that. And what that means is, if you look up here at this point right here, that point is telling us that basically at 4.00 seconds, x was equal to 6.00 meters. So from that, you should get an idea that the height of a data point, equals the position, or depending on how you're writing it, distance traveled. Okay. So that's what dots on a graph mean. When you're actually graphing, you're finding solutions of some equation. In principle, this particular line has an equation associated with it. In fact, the equation for a straight line is y equals mx plus b, where m is your slope and b is your y-intercept. Okay, so in this case, the intercept is 0, and the slope appears to me to look like 1.5 over 1, which is 1.5 meters per second. Does anybody have any idea, based on the unit that I just said, what the slope means?
It's your acceleration.
Close. It's your actual velocity in this case. So you'll see later we have a scenario where that's true, but on a x versus t graph, the height is the distance from the origin, and the slope is the average velocity. And I say velocity here, not speed, for a good reason, because sometimes your slope, your graph can look something like this. So right here, the slope is positive, whereas right here, the slope is negative. So it actually includes not only the magnitude, but it also includes the direction. A negative slope would indicate it's going back towards the origin, whereas a positive slope would mean it's going away from the origin. And that graph turned out really ugly. Let's draw it again. So the slope right here is just that quantity, but the slope right here, say, it's just that quantity. So you can see how those slopes come into play. If our curve was actually, if our graph was actually curved, we could see it being a little more complicated. So let's look at another one. What if I had, I'm going to say a position versus time graph again. What if I had a curve that looked like that? Okay. Well, it turns out you guys already have an idea of how to calculate an average velocity. Have you ever done that, like with a with an odometer in your car or something like that? Or used signs on a trip? You know, it says 28 miles to Busch Gardens, and then later on you check your watch and your when you run into the next sign and it says 10 miles to Busch Gardens, you know you've traveled 18 miles since the last sign. And if you divide that by the time, you get your average velocity. I do that all the time, which is probably part of the reason I'm a horrible driver. I find driving a little too boring, all the crap that can be watched at the time. So I often come in near wrecks and stuff like that. So I need to stop doing that. But anyways, luckily I have a car that takes care of that now. I've got a new Honda that like slows me down when I get on anybody's tail, or it pulls me back into the lane when I swerve. So it's a little scary sometimes when it does it, but it's probably for the better. So if you're thinking about, for instance, what about this time right here? Let's draw a blue line down to time t1, and let's say to this time right here, which is time t1 plus delta t. Okay. Now, if you really wanted to know the velocity at t1, you'd really want to know the slope at that point exactly, because we said the slope is the velocity. But if we take the slope between these 2 points, then you could say this is x of t1 plus delta t for the rise, in other words, minus x of t1. And then this part right here is t1 plus delta t minus t1. So you can see the slope, m, would be x of t1 plus delta t minus x of t1 over basically just delta t. Does that make sense to everyone? Now, that slope looks pretty good, but if I'm actually looking for what I think is the best slope, I would say it's probably that quantity right there. Would y'all agree? See how it's slightly angled a little steeper than the blue one? Well, if I took the limit from calculus as delta t approached 0 of delta x over delta t, which that's really what delta x is here, then I would actually get the actual velocity. And we call it v instantaneous. Okay. And of course, from calculus, we know that that means v instantaneous speed, which is what your speedometer reads every time you just look at it for a quick second. V instantaneous is dx over dt. Any questions on that? So the generalization, if you will, of saying the slope on x versus t graph is the velocity, or the average velocity, is that the slope at any instant on the x versus t graph is the velocity at that instant. So that's instantaneous velocity compared to the average, which is distance traveled divided by time taken. Okay, now the average is still very useful. I don't really like the way that turned out. The average is still very useful. I use it on my trips all the time, again, because I like to avoid actually doing good driving. But I'm constantly calculating what is my average speed. Good Lord, that was horrible. I'm constantly calculating my average speed, the total time taken, stuff like that. So it does come in handy, because it sort of cuts out details like you stop for a bathroom break, or you stop to smoke a cigarette or whatever, right? So the average velocity is always going to be the distance traveled divided by time taken. Well, let me rephrase that. Average speed, technically. Right now, since we're only doing one dimension, we're sort of teetering back and forth between realizing that speed and velocity have different connotations. One of the connotations is that the average velocity is your a vector that points to your final position minus a vector that points to your initial position. And for instance, if you hit a home run and you accidentally step on home plate running to first, then when you get back to home plate, your total distance traveled is significant. Obviously, it's 4 times 90, right? But your displacement at that point, which is your change in position, which is what you use for average velocity, that's actually 0 because your position hasn't changed. So it's dangerous to treat average velocity at average speed as the same, because in fact, average velocity can be 0 even when the speed's quite different, because the average velocity is the just the change in displacement divided by time taken. Whereas average speed is just the distance traveled divided by time taken. Any questions on that? So if you drive, for instance, what is your average speed if you cover, let's say, 180 kilometers in 3.00 hours? Y'all should be able to do that, right? Actually, let me. Why did I do that? Now, I don't want you memorizing this formula. That would be absurd. All you got to think about is if you happen to drive a car at all, or even have a bicycle with a speedometer on it, all you have to do is look at your speedometer and it says what units are on your speedometer.
Miles per hour.
Miles per hour. And mile is a unit of? Distance. And hour is a unit of?
The other one.
Time. Yep. And of course, per means divide. So you automatically should know that the average velocity should be distance divided by time, just like your average miles per gallon is divide the miles you drove by the gallons you use. So in this case, we're going to get 180 kilometers divided by 30 hours, which gives us 60 kilometers per hour. And that's actually kind of low, but that's a typical average speed over a long trip on the interstate. It's more likely that now that speed limits are 55 and up all over the place on interstates, it's more likely that you're averaging closer to 60 miles per hour as opposed to kilometers per hour. But still, I think you get the point. Now, if we had X is equal to, let's say, 3.0 meters plus 4.0 meters per second every second times t, what then is the velocity? Does anybody know what you're going to do to find the velocity as a function of time? Well, if you take the derivative of 3.0 meters, the meter is just a unit. It's being multiplied by the number 3, but it's a unit, so it's a constant. So that disappears. However, the plus 4.0 meters per second every second times t, that's a constant times the time. So I'm going to get that it's 4.0 meters per second every second. And that's supposed to be my, oops, that's a bad unit. Remember me telling you about all equations have to be dimensionally correct? I was thinking I was doing the next problem. That's why I made that boo-boo. I'm going to fix this real quick by erasing the meters per second down here. Yep, that's close enough. Okay, so then I'll do it here as well. Yeah, I get it. All right, so yes, the velocity is dx dt, which is the derivative of x as a function of time. And you might think that's really weird, you know, how are you going to be out in the real world and all of a sudden somebody gives you a function that's the velocity or position as a function of time? You can't, right? That's just not going to happen. But as you'll see in lab, no, that is actually something we can do now. We have motion sensors. We have motion detectors. We can they can actually be worked in the lab, but you can also put them in security systems and track where people are going, all sorts of good stuff. So it is actually now a time where we often get position as a function of time. And they've been doing that for years. In fact, like if you worked with a steam engine in the late 1800s, early 1900s, there were mechanical devices that would print out pictures of pressure versus velocity and all sorts of stuff like that. So in that sense, you always had the ability to do it, but back then it was mechanical. Now it's just electronic. Now, what I'm asking you in the second part is what is the velocity at 3.00 seconds? Well, notice that the velocity actually has no time dependence because it was only, the position was only linear in time. So once you take the velocity, it's that constant in time. So you get 4.0 meters per second is the actual velocity at 3 seconds, but that's the same thing as the velocity at 20 seconds, at 18 seconds, or at 0.03 seconds. So any questions on that? Now,
Yeah,
go ahead.
where do you get 3 seconds from? I see 3 meters, but where do you get the 3 seconds?
I just made
Is
that
it just
up.
a question that you?
Yeah, it's part of the question. I just made it up down here.
Okay.
Yeah, I was just, pulling out numbers just to give you an example. Now, one thing, it was really Galileo that sort of started off all this, because before Galileo came along, we didn't really have a good idea about, or even an idea of velocity and acceleration. He was basically threatened at the Inquisition, where he had basically had written a book suggesting that the position of the church was held by a guy by the name of Simplicio, which is, basically for meaning a simpleton. And that was the Pope's position, obviously. And because he wrote that book that way, some of the cardinals were like, hey, I know the Pope's, I know Galileo's your friend, but he's kind of treating you like you're an idiot. So you might want to stamp that down. So they basically ultimately did. And he was forced to recant his idea that the planets orbited the sun. And he ostensibly said, yet they do, or something like that as he walked out. We actually have the transcripts of that. You can go to the Vatican and see the transcripts of that whole trial. And that part's not there, obviously, or he probably would have gotten more trouble. But he was ordered to in-house arrest for the remainder of his life. He was already going blind. And he probably got off the hook that way because he happened to be a friend of the actual popes. But either way, Giordano Bruno had just been burned at the stake for something not unlike what Galileo had done, what Galileo was shown to have done in his trial. So he just said, well, I'm not allowed to teach astronomy, or what they would have called maybe astrology back then. He's not allowed to teach that anymore. But he had discovered some neat things, and it showed him that he didn't really understand motion. So he spent the rest of his life studying motion. And what he realized is when you let a ball roll down an inclined plane, it speeds up. When you let a ball roll up an inclined plane, it's slowed down. Therefore, if it rolled along a perfectly level plane, it should be able to just roll forever at a constant speed. So he said, well, the motion of an object is actually normally whatever its motion is. It's not like Aristotle said that all motion tends to come to a stop. There was a whole set of laws that Aristotle had worked out. And by the time of Galileo, the whole church had adopted them and interpreted all of Scripture in terms of them. But he was brave or crazy enough to say otherwise. So he decided he was going to study motion. For instance, he had learned that the satellites of Jupiter were actually following Jupiter. So that already showed us that Aristotle's rules of violent versus natural motion were not valid. So he said he'd really like to know whether when you drop an object, is it instantaneously going that fast and falling the same speed all the way down, or is it speeding up? So he studied those inclines. And when you study an inclined plane, you can use trigonometry to get back what would happen in a straight vertical motion, because it's just a component of the vertical and the horizontal motion that make up an inclined plane problem. And from that, he discovered that objects actually speed up when they're falling, and they speed up independent of mass. So that was a really big deal. And he basically defined the concept of velocity and the concept of acceleration. And he defined it such that constant velocity is that motion that covers the same distance in the same time. So if you consistently cover a distance of 1 meter in 1 second, your velocity is 1 meter per second. But if you find some other time where there's a 1 second interval and you cover 1.3 meters in that time, then that's not constant velocity. So the very definition of constant velocity is to cover the same distance in a certain amount of time, no matter what part of the motion you're studying. Then he discovered, like I said, falling balls were actually accelerating. And what do you mean by accelerating? He said that basically the change in velocity that occurred over an interval of time, if that was a constant for all of those intervals of time, then that's constant acceleration. So a constant acceleration is an acceleration where an object changes, say, from 1.0 to 1.2 meters per second every second. So if after 1 second it goes from 1.0 to 1.2, then after 2 seconds it goes to 1.4, and after 3 seconds it goes to 1.6, and after 4 seconds it goes to 1.8. So it's consistently changing this velocity by 0.2 meters per second every second. And that's the way I want you to use the units, or I want you to state the units for acceleration for a long time until you get the feel of it. For instance, we're going to learn that the acceleration due to gravity is 9.8 meters per second every second. That's the way you should say it, even though you can write it mathematically as 9.8 meters per second squared. It just doesn't mean very much physically when you say it meters per second squared. So now that we have sort of that idea in mind, that constant velocity travels a set distance for a set time, and actually if it's constant velocity, it's not going to change direction either. So I'm going to put slash speed. For instance, if it goes if it's found to travel 2.0 meters in 0.10 seconds, then S equals V equals 2.0 meters per 0.10 second, which you could also interpret as 20 meters per second, just because the math allows you to do it. So you can say 0.2 meters per 0.1 second, that's a velocity, or you could say it is 20 meters per second, and that's acceptable as well. Constant acceleration, on the other hand, changes the speed by a set amount each chosen time interval. So for instance, switch to eraser. So, for instance, a constant acceleration changes the speed by a set amount each chosen time interval. So we're talking here, in this case, I chose the time interval to be 1 second. So for instance, if your velocity changes by negative 10 meters per second each second, then A is negative 10 meters per second, which is pretty close to what gravity does. And what that means is if you toss a ball up at, say, 30 meters per second, then if there's no air resistance, then essentially the ball is going to go from 30 to 20 meters per second after 1 second. And then it's going to go from 20 meters per second to about 10 meters per second after 2 seconds. And then it's going to go from 10 meters per second to 0 meters per second after about 3 seconds. And then it's going to start falling downward. So its velocity is going to go from 0 to negative 10, which means the downward direction. And then from negative 10 to negative 20 meters per second. And then from negative 20 to negative 30 meters per second. And that total time would take 6 seconds. And that's exactly how acceleration behaves, except it turns out it's closer to 9.80 instead of 10 meters per second. Okay, so now we've got some idea of things or how acceleration and velocity differ. Can anybody tell me what the most sort of exact and reliable technical data a car manufacturer or a car salesman can give you regarding a car's acceleration?
Horsepower.
Horsepower is one of them. That's not as direct as I'd like because, for instance, a Mack truck has a ton of horsepower, but it's so heavy it doesn't have much acceleration. Can anybody think of another one?
Torque.
Torque's another one, yes. But again, just like the horsepower, a large torque is needed to push a Mack truck, but they don't have much acceleration. There's something that sounds
0 to
like
60 time.
There you go. That's the one I was looking for. Oh, and all of y'all were right, by the way. Yeah, they all bear on it, but really you have to compare it to the weight to get it done. But the most direct way is your 0 to 60 speed. So an example of acceleration, if I can ever get it straight again. My pen just stopped writing. There it is. It's just being a hole. So example. Now, I'm not telling you by any stretch of the imagination that this acceleration is constant, but let's say a Mustang from 0 to 60 miles per hour in 4.00 seconds. So the acceleration would be 60, and I'm going to go ahead and pretend there's an extra sig fig, miles per hour divided by 4.00 seconds. So that gives us 15.0 miles per hour per second. And that's a nice unit. It's ugly, but it's a nice unit because we really get a feel for it. What I'm saying when I write that is if this was truly constant acceleration, and again, it's not constant acceleration, then in the first second, the Mustang would go from 0 to 15 miles per hour. In the second, it would go from 15 miles per hour to 30. In the third second, it would go from 30 to 45. And then in the fourth second, it would go from 45 to 60. Now, what probably happens is it goes considerably more than 0 to 15 in the first second, and considerably more than 0 to 30 in 2 seconds. But then it goes considerably less than changing by 15 in the third and fourth second. But in principle, if it kept on like that, it would go next to 75 miles per hour after 5 seconds, and then 90 miles per hour after 6 seconds. Okay, that's what acceleration does. It changes velocity, and if the acceleration is a constant, it's going to change the velocity by a constant amount each second. So, for instance, anybody heard about the Tesla? I think it's called like flannel or something. This is amazing. This has a 0 to 60 in 1.2 seconds. It's called the S Plaid. That's what it was. Tesla S Plaid. The Tesla S Plaid, P-L-A-I-D, I guess. That actually has 0 to 60 in 1.2 seconds. And you can find it online. It's quite awesome. But if we want to calculate that that acceleration, all we have to do is say the Tesla. Is that word plaid? Do y'all agree that that's plaid? I haven't heard anybody actually physically say the word, so I don't know if I'm pronouncing it right.
Yeah, that's it.
And I'm not very good at spelling the word plaid because I've never written it down before. So anyways, so that's the car. So it goes 0 to 60 in 1.20 seconds. So the acceleration turns out to be, from that very example I gave you, we can say the average acceleration is delta V over delta T. Right? That looks just like the average velocity, which was delta X over delta T. So we're going to say this went 60 miles per hour minus 0 miles per hour. That's what, remember, whenever you see this triangle in front of that V or in front of that T, that triangle like that means change in. It's supposed to say, hey, when you see me, write final minus initial unless your teacher tells you otherwise. And that divided by 1.2, you can say that 1.2 is 2 times 6 divided by 10. And then that would get you a nice, neat number, but I'm not going to mess with that, with those tricky little arithmetic tricks, because time's getting late and I don't want to screw you up. So I'm going to do 60 divided by 1.2, and that's going to give me 50 miles per hour per friggin' second. Check that out. Imagine now if you did that for 4 seconds, and assume that the Tesla could really do that for 4 seconds, then it goes 0 to 50 in 1 second. It would go 0. Wait a second. That can't be right. Yeah, that makes sense because it's 0.2. It would go 0 to 100 in 2 seconds, 0 to 150 in 3 seconds, and 0 to 200 in 4 seconds. So that's a really big deal. But again, that's just an example. Now that we have an example, I'm going to show you something neat that we can use to give us some fundamental equations, because we know that V average, which we can just put a bar over it if we want to know average, is just delta X over delta T, and then V instantaneous equals dx over dt. We also say that A average is equal to delta V over delta T, but we'd say that A instantaneous is dv over dt. So if you make a plot, for instance, of velocity versus time, the slope is A. Okay, but the height is the velocity. And by height, I mean distance from the horizontal axis. If it went down, it would be the distance from the horizontal axis. But because that's negative, that's just telling you it's going towards the origin instead of away from it. So now that we have that, let's imagine A equals a constant. And we'll say V equals V0 at T equals 0. And we'll say X is equal to X0 at T equals 0. So we can say A equals dV dt. I can multiply both sides by dt, and I'd say A dt is equal to dV dt dt. That's a differential equation. I'm going to integrate it from t equals 0 to t. And this is going to be integrated from v equals v0 to v of t. And obviously this a being a constant just gives me at plus, or excuse me, equals v of t minus v0, or you can say v as a function of t is equal to v0 plus at. So this is for a equals a constant. notice how I put in that V0 as one of my initial conditions. That came from this part right here. Now I can say V of t, or I should say, excuse me, I wanted to find x of t. Well, that's equal, of course, or that's related to v of t equals dx over dt. So I can do the same thing again. I'm going to say v0 plus at is equal to dx over dt. I'll multiply both sides by dt, and I'll take the integral this time from t equals 0 to t, and this time from x equals x0 to x of t. And on this side, I get 1/2 at squared plus v0t equals, this side I just get x of t minus x0. So here I have x is equal to 1/2 at squared plus v0t plus x0. And that's another one of our super valuable kinematic equations. Okay. As is this, well, actually, as is this, and this. And in fact, that's nice, but what if you want to know, say, the final velocity without knowing the time? Or what if you want to know the final position without knowing the time? Well, that's actually not too bad, because I'm going to call this equation 1, 2, 3, 4, 5, and 6. What I'm going to do is I am going to solve 5 for t and plug it into 6. I literally picked up my iPad like I was going to turn over the page. I'm so old. Okay, so solve 5 for t and plug into 6. Well, v is equal to v0 plus at gives me t is equal to v minus v0 over a. So I'm going to call that 5 prime. Allie, stop it. My cat's going crazy. Now I'm going to plug that into 6. So 6 is going to be x equals 1/2 a v minus v0 over a squared plus v0 v minus v0 over a plus x0. So I can manipulate this a little bit and see that when I square this v minus v0 squared, I'm also going to square the a in the bottom. So it's going to be 1 over 2a times v squared minus 2v v0 plus v0 squared. And then if I distribute the v0 through the second term, I'm going to get v0 minus v0 squared, over a plus x0. Now I want to get a common denominator. So I'm going to say v squared minus 2v v0 plus v0 squared over 2a plus 2v v0 minus 2v0 squared over 2a plus x0. And now I can say x minus x0 is equal to v squared minus 2v v0 and positive 2v v0 is going to cancel out. And v0 squared minus 2v0 squared is going to be minus v0 squared, all that over 2a. So finally, I have v squared is equal to v0 squared plus 2a x minus x0. And this will be our kinematic equation number 7. Now, some physics instructors don't allow people to use this at all, especially in the calculus-based physics, because it's an equation that's not a vector equation. X equals 1/2 a t squared plus v0 t is one of those vector equations. But in my class, I let you use it, and that's how that was derived. Now, the whole reason for me showing you all this stuff is I wanted you to understand how we came across these equations. These kinematic equations are going to be used over and over and over again. And when you use them, I suggest you try to imagine a coordinate system, an X versus time, for instance. Imagine an origin and assume the X-axis is pointing to the right. Maybe the Y-axis is pointing up. Maybe it's an X versus Y coordinate system. Maybe it's an X versus T coordinate system. But the main thing is make sure you make a coordinate system and start figuring out which directions these quantities that have directionality, like acceleration, like velocity, like a force, they have a directionality associated with them. So anything that points their direction, if that direction happens to be the positive direction, then it's going to be positive. If that direction happens to be the negative, it's going to be negative. Now, there's one other equation that is also true. Notice all these required A equals a constant. And when we had A equals constant, that gave us A equals A bar equals dV dt. And we had A is equal to V minus V0 over T. We also had V is equal to V0 plus AT. And we had X is equal to 1/2 a t squared plus V0 times T. And I hate what I just did with that exponent of 2. I'm so obsessive compulsive. I ruin everything. Plus X0. Those all required A to be a constant, but then there was also this definition that V instantaneous is equal to dx over dt. And I'll say definitions, and A instantaneous is equal to dV dt. And then V average is equal to distance divided by time. Okay. Well, it turns out there's one more equation, and that's V0 plus, or let's say it differently. So that one comes in handy every now and then. You never have to use it, to be honest with you, but sometimes it can be a short trip. But all of these require that A be a constant. So all of these require that A be a constant. But you don't always have to have A equal a constant. So we got 5 minutes left. Let me show you an example. What if A of t was equal to 2.00 meters per second every second plus 3.00 meters per second cubed t, like that? Well, that means I'm going to forget the units for right now. We know what they are. So we're going to say A of t is equal to 2.00 plus 3.00 t, but that's also equal to dV dt. And if we assume x equals 0 at t equals 0, we assume v equals v0 at t equals 0. Let's say v0 equals 6.00 meters per second. Then we can do this the same way. We're going to say 2.00 plus 3.00 t dt is equal to the integral of dv over dt from t equals 0 to t. And this is from v equals 6.00 meters per second to V of t. So in this case, I'm going to get 2.00 t plus 3 halves t squared. Actually put the range of integration on the wrong one, on the wrong intervals like a bonehead. But anyways, you got that. So this one's going to be V of t minus V0, which is 6.00 meters per second. I can't believe I did that. Let me fix that real quick. All right, that's my watch saying we got 2 minutes left. This, as I said, was from t equals 0 to t, and this one was from V0 equals 6.00 meters per second to V of t. Okay, so now you got V of t is equal to 3 halves t squared plus 2.00 t plus, actually, I'm going to go ahead and put the 6 in there. And that's also equal to dx dt. So now I can say the integral of 3 halves t squared plus 2.00 t plus 6.00 dt is equal to the integral of dx over dt, and that integrates from x0 equals 0 to x of t, and this integrates from t equals 0 to t. So this first 3 halves t squared is going to become t cubed, so that'll be 1 half plus 1.00, that's a 1, t squared plus 6.00 t is equal to x of t minus 0, or x of t is equal to 1 half t cubed plus 1.00 t squared plus 6.00 t. Now, this is an answer to the problem, but that's not something we'll use because that was for a very specific case. But that's what part of the reason I'm showing why and how we derive those kinematic equations. This is for a very special case where the acceleration was given as a function of time, and I just used the same process that I did to come up with my kinematic equations, only in this case I came up with a different set of kinematic equations. So that's it, folks. Time's up. We've finished a big chunk of chapter 2 now. Let me know again if y'all have any problems with those dimensional or unit analysis problems, or with those estimation problems. Like I said, I gave you videos to watch instead of me covering that, and I've given you a little bit of stuff on how it's done. But I will definitely be free to have a private meeting with you or have a group meeting with everybody to work on that. You can also just talk to your lab instructor; she might be able to help you as well. So. You guys are free to go. I'll wait for the last one in case anybody has any questions. Thanks for coming, everybody.
Does TCC have a tutoring center for this?
Yes, the last I checked, they did not have they didn't have a decent tutor. They only had a person that was currently taking the class, and though the person was really good, they were figuring out at the same time, maybe they have somebody better now. But our adjuncts are good. Our lab instructors normally are pretty good. And like I said, I'm willing to work with you if you need a specific time, or if we can just find some time.
Unfortunately, the only time you have available for your office hours, I work almost every time.
That's
so.
okay. Just we can do it one night after class, or on a Friday. I'm open all day. I'll find a way to accommodate you.
Jamie, I have a tutor for you. I'll let you know.
Oh, that's good. Thank you. Is that Bianca that said that?
Yeah, that's me.
Okay.
Thank you.
Bianca, thank you.
Okay. Have a good evening.
You too. And like I said to her, everybody, if y'all need me and it's not during my office hours, that's okay. I give you my office hours because I'm available then. That's not the only time I'm available. I definitely want to help you as much as I can. Anybody else?
Have a good night.
You too. Thank you.
I'm not sure if I missed it. I did have a question about the extra credit. I was looking at the grades, but I never was able to access the extra credit to complete it.
The ones on, you talk about in MyLab and Mastering, or you talk about in Canvas?
It's in Canvas. It has like a February date, so I wasn't sure if it was an error.
Yeah, that's definitely an error, but that might have been one I
Okay.
hadn't signed yet because some of them are left over. I thought I made them invisible. I'm going to check in there right quick and see what it is. I have extra credit for week 1. I don't think I had any in week 1.
Okay.
Yeah, there wasn't any for week 1. Let me see if I put any for week 2. Yeah, that was something that was just there. It wasn't necessarily extra.
Okay.
It was one that was from a previous semester, so that's why.
Okay. Yeah, it said missing, and I never saw it, so I wanted to make sure it wasn't something that I overlooked.
I'll tell you what I'll do is I'll put for this week, I'll put the extra credit. I sort of hinted to it when we were doing chapter 1, but I never actually formally for this class made an assignment. But if the standard unit of a kilogram is a cylinder, it's made of platinum iridium, and to make it less likely to succumb to corrosion, changing its weight and everything, they minimize the surface area. That's a nice little neat calculation you can do, and I will write that up for you if you wish to do it, and you can turn that in as by the beginning of next week or maybe Wednesday of next week. I'll put it on week 2.
Okay, thank you.
You're welcome. Anybody else?
Yeah, I guess I'll talk to you whenever everyone leaves. I can't tell on my phone right now.
Yeah, we've got a couple people left. Antoine, are you still here? And Famada, are you still here?
I'm still here.
Did you have a question?
I'm leaving now.
Okay, thank you. Famada, did you have a question, sir?
I had a question about my enrollment. They actually dropped me from this class because I didn't have my financial aid in.
Gotcha.
But I submitted it earlier today. They said they're gonna.
Antoine, what's your last name?
Robinson.
It's still showing you not there yet, but it will probably be there after midnight.
Okay.
Yeah, I'm looking at it right now. Your name's not in there now, but one of my previous versions I recorded did have your name in it, so it'll pop up there. And like I said, you should see it tomorrow morning. Okay.
Okay. So should I just like wait because I can't